Hello everyone. So this is the fourth lecture on thermodynamics, and in this lecture we'll complete the theoretical portion with second law of thermodynamics and its associated terms. Okay. So first of all, let's start today with enthalpy. Okay. So enthalpy is a, we can say, parameter which depends on internal energy and PV work done. So it is given as H is equals to U plus PV. If we just take delta, change both the side, it will look like this. Now delta H is equals to delta U plus delta P delta V plus V delta P. Okay, next we have, suppose this is a chemical reaction. What is actually the, what you say, yeah, Ng. This is called delta Ng is the concept. Delta Ng is actually the number of moles of gaseous product minus the same of reactant. Suppose all are gaseous species. So we'll write delta Ng as C into what? C plus D minus plus B, like this. Okay. Now for a chemical reaction, how we write enthalpy? Delta G is equals to delta U plus delta NgRT, where R is universal gas constant, T is the temperature, delta Ng we discussed earlier. Okay, so this is the formula, this is the equation which is used in the chemical reaction while dealing with chemical reaction. Okay, so this was the term called enthalpy. Now we will discuss entropy, and with this we will start the second law of thermodynamics also. Entropy. Entropy is what is? It is actually the disorderness or randomness. So it is actually the disorderness or randomness of the motion of particle within the system. It is denoted by S, especially we define delta S, that is change in entropy. Okay, so first of all you have to understand this. Now this entropy increases with increase in number of moles. Also for gas, liquid and solid, we see entropy is maximum in gaseous phase, then in liquid, then in solid. Because in gaseous phase the randomness is there, maximum randomness is there in gaseous molecule, not such intermolecular or intramolecular force of attraction is strong. Okay, particles are free to move, so randomness is more, so entropy is more, because entropy is nothing but the measure of randomness or disorderness. Okay, so here we go with the entropy. Now what actually is second law of thermodynamics? It is actually the measure of reactions as spontaneity. What do you mean by spontaneity of reaction? The tendency of a reaction to occur by itself without any external agent, or without any external, you can say, help. It occur by its own. That is spontaneous reaction, which occur by its own. If it is required, if some external heat supply is required, then that is not spontaneous. That is not spontaneous. That will be non-spontaneous. So actually the second law of thermodynamics is a measure of reaction spontaneity using some terms like entropy, Gibbs free energy, right? So this is the concept. Now what actually happens here, we have an you can say a concept, that is spontaneity, that the reaction is occurring on its own without help or supply, without any external help or supply. Okay, so if the change in entropy is positive for a system, okay, then you can say that it is a spontaneous process. Spontaneous process. Okay. If it is less than 0, it is called as non-spontaneous process. Okay. So actually we discuss about spontaneity of reaction using entropy. Okay. Now this is a very basic, you can say, definition concept of entropy. In more advanced version we discuss in a more detailed way. So there are some other ways to define entropy of a system, that is integrand dq reversible by T, where dq is the heat exchange in the reversible process, which is, you can say, can be actually at reversible process we have equilibrium. Okay, whenever we talk about reversible process there is a concept of equilibrium, but here we will not talk about that. Here we will just keep in mind that actually the delta S is defined as dq reversible by T. Okay, now for different processes, so for different processes there is a general formula. This is called the general formula of entropy, which is NCV ln T2 by T1. T2 is the final temperature, T1 is the you can say initial temperature, like this. NCV ln T2 divided by T1 plus NR ln V2 by V1. Okay. Now we will take this formula into the consideration and we will just find the expression in different processes. Okay, where this entropy is calculated. Okay, now first of all we will talk about the process that is isobaric process. In isobaric process, pressure is constant, volume is directly proportional to temperature, so we can write V1 over V2 is equals to T1 over T2. Okay, now talking about entropy, so it is actually you can say NCV ln T2 over T1 plus NR ln V2 over V1. Now just we will uh, put V2 by V1 equal to T2 by T1 and we will take it common. It will be like this, and ln T2 by T1 and CV plus R will be CP. So NCP. Okay, I hope you getting this. NCP ln T2 by T1. This is for the uh, isobaric process. For isobaric process. Now isochoric process. Volume is constant, so V1 will be equals to V2. So ln V2 by V1 will be what? It will be ln1, and since ln1 is 0, so delta S of system will be what? NCV ln T2 by T1. I'm talking about NR ln V2 by V1, so that term will be 0 because ln V2 by V1 is 0. So it will be NCV ln T2 by T1. Since volume is constant, so pressure is also directly proportional to temperature for a constant mole of number of moles. Okay, so we can write here like this also. Okay, this was our isochoric process. Now we will discuss about isothermal process. What actually happens in isothermal? Temperature is constant. T1 we write or T2 we write, both are same. So again ln T2 by T1 will be ln1 equal to 0. So in this case, pressure is inversely proportional to volume, and we will write delta S of system as nR ln V2 by V1, because that term of temperature ln T2 by T1 will be 0, and now we will write nR ln P1 by P2 like this. Okay, so this is our basic formulation for isothermal process. For adiabatic process, it is quite obvious and quite easy that using this definition rather than using that in this the heat exchange is 0, so entropy will be 0. Okay, some more you can say from advanced, or you can say a little more obvious, but you have to remember this, that for fusion process, delta S of fusion will be delta H of fusion over freezing temperature. Then for vaporization it will be like this. For sublimation it will be like this. I think you got these points. Okay, now we will introduce Gibbs free energy. What is actually Gibbs free energy? Again, it is a thermodynamic parameter which is intensive in nature, which is extensive in nature, means it is additive, and we express it in terms of its change delta G, that is given by delta H minus T delta S. Okay, or we in differential form we write dG is equals to VdP minus of S dt. Okay, so this expression is very important, and actually when we talk about equilibrium also, the Gibbs free energy being an extensive property, entropy is an intensive property, Gibbs free energy an extensive property. So the spontaneity of reaction and non-spontaneity, equilibrium, condition of equilibrium, all are derived from this particular equation, which is called Gibbs-Hamilton equation. Like this it is called, but it's more important is this equation rather than its name. Now let's discuss about it. This is our equation. Now for spontaneous process, always remember delta S is greater than 0 and delta G is less than 0. It means delta H minus T delta is less than 0. So delta H, in this way we can write, and temperature will be greater than delta H by delta S. So there is a condition for spontaneity. Okay, talking about non-spontaneity, so just we have to change the inequality sign, or we can derive again. So for non-spontaneous process, as we discussed, that entropy is actually talking about a spontaneity of reaction, randomness, disorder, and spontaneity of reaction. So delta S will be less than 0, delta G will be greater than 0. So we will write delta H minus T delta S is greater than 0. So temperature is actually here. You can say like this, delta H is equals to T delta S. So temperature is actually less than delta H by delta S. Right? I hope it is clear to you. Okay. Now for equilibrium, what happens actually? For equilibrium, delta G is 0, so delta H is equals to T delta S. Temperature is given by delta H by delta S. These are very important results which you must remember. So yeah, this was our concept of Gibbs free energy, and the concept of what we say entropy and all for spontaneity of reaction. Now one more thing is your process of adsorption. Here delta S is also less than 0 and delta G is also less than 0. So as a special case you may remember this. Now we are just on the last of the today's class, third law of thermodynamics, just a basic intro. That is said that when temperature is reaching to 0 Kelvin, the entropy of perfectly crystalline solid, what is crystalline, what is amorphous, we'll discuss later on in the course of solid state. The entropy of perfectly crystalline solid is also it also tends to 0. This is what actually the third law of thermodynamics, very basic introduction you should have. Okay, so temperature is reaching to 0 Kelvin, which is obviously not possible. It is just so we use tending to, no, otherwise we may write temperature equal to 0, but equal is not possible, it's just tending. So if temperature is tending to 0 Kelvin, then your entropy of perfectly crystalline solid will also tend to 0. Okay, so this was our today's lecture. That is, we discussed about entropy, we discussed about enthalpy, we discussed about Gibbs free energy, and we discussed the expression of entropy in different cases. Okay, so and lastly we discussed third law of thermodynamics. Okay, so thank you so much for joining me in this session. In next session we'll be having the discussion on challenging test, which I'll give you very soon. Okay, till then, bye bye. Exiting 1 2 3. Next chapter, what will be the next chapter, that I'll also tell you in community post. Thank you.